Hello everyone, and thank you for viewing my video. Today I will be presenting my cybersecurity GPG Cryptographic Toolkit. I hope everyone is having an amazing day. This project was built not only for fun, but also to make common cybersecurity tasks easier when working with GPG, a cryptographic tool used to support confidentiality, authenticity, integrity, and non-repudiation. Normally, when using GPG in its original command line form, cybersecurity professionals would manually type commands to perform actions such as generating SHA-256 hashes for files, creating asymmetric key pairs, digitally signing hash files with a private key, verifying digital signatures with imported public keys, and encrypting or decrypting files using encryption algorithms such as AES-256. My application was originally designed to make the non-repudiation process easier by providing a graphical user interface for GPG-related tasks. Over time, the project evolved into an all-in-one GPG Cryptographic Security Toolkit that allows users to execute GPG operations through interactive clickable buttons instead of manually entering commands in the terminal. I understand that there are already other applications that enhance or simplify GPG functionality. However, this project is different because I built my own customized tool that I can personally use for cybersecurity practice demonstrations and workflow automation. For me, this project represents my interest in creating and modifying cybersecurity tools that are practical, educational, and useful in real-world security workflows. Overall, this project demonstrates both security analyst knowledge and security engineering implementation skills by combining cryptographic concepts with working software tools designed to make cybersecurity tasks more accessible and efficient. Non-repudiation basically means that someone cannot easily deny that they performed a certain action. For example, if a person signs a document, sends an approval, or submits a file, there should be proof showing that they were the one who did it. My tool demonstrates this using core cryptographic concepts such as hashing, digital signatures, public and private keys, and trusted public key verification. First, the user selects the button called Compute SHA-256 hash. After that, I press the button to load a file. For this example, we are going to use a dummy signed non-disclosure agreement document. Maintaining the integrity and authenticity of this non-disclosure agreement is important because multiple stakeholders may handle, review, or rely on the document throughout the chain of custody. Now I'm going to locate the full file path for that dummy example. Alright, so I'm going to paste the file path for the document within my Compute SHA-256 interface. Now we are going to press Open, and you will see the file loaded onto the screen. After the correct file is loaded, we can proceed by pressing Create Hash. After we press Yes, the application computes the SHA-256 hash. The hash was successfully created. Now we can view the hash we created in a separate interface I built for storing computed hash files called Stored Hash Files. A hash is like a digital fingerprint. It represents the exact contents of a file. If even one small part of the file changes, the hash value will also change. This helps prove integrity because we check whether the file stayed the same or was modified. For example, if I send a contract to someone and create a hash for it, that hash represents the original version of the contract. If someone changes the contract later, the new hash will not match the original hash, which shows that the document was altered. In the stored hash interface, we can view the hash fingerprint identifier. I can also export a copy of the hash file into Windows File Explorer. Or I can delete the hash file if I no longer need it, but for this example, I still need the hash file. Now we are going to switch over and explore another useful interface I created called asymmetric key generation. In the asymmetric key generation interface, you can create an asymmetric key pair by pressing create new private/public key pair. Next, you type the same password twice to protect your private key, similar to how GPG works in the command line. Now we can set the expiration date for our key pair. For this example, I'm going to set the key to have no expiration date. All right, now I will assign the real name for this key as John Doe. Now we will set the email address to chalevpenetration@gmail.com. For the comment, we will type GPG Security Toolkit demo key. There we go. We have successfully created our asymmetric key pair. Now we can use the newly created private key to digitally sign files in the future. And we can share the public key with other users so they can verify our digital signatures. I also added a few other key management capabilities within the asymmetric key generation interface. If you press the revoke button, you can select one of the public keys that belongs to a key pair and revoke it using the corresponding private key. This is useful if the key pair has been compromised before its expiration date. After a key has been revoked, anyone using that same public key in GPG can check that the key should no longer be trusted. As you can see, the public key is now labeled as revoked. In the interface after I confirm the action. Lastly, this interface also gives you the option to delete any key pair that is no longer needed. I will not be deleting any keys today. After creating an asymmetric key pair, Now I am ready to create a digital signature within the interface called Create Digital Signatures. The private key is something that should only belong to the person signing the file. When the file is signed with the private key, it helps prove that the file came from that person. This supports authenticity because it helps verify who signed it. The matching public key can then be used to verify the signature. The public key does not need to be kept secret. Its job is to check that the signature was created using the correct private key. So, as an example, if I send a digitally signed contract to a client, they can use my public key to verify that I was the one who signed it. If the signature is valid and the hash still matches, then we know two things. The document came from me and it has not been changed since I signed it. That is where non-repudiation comes in, because the file was hashed and digitally signed with my private key. There is now proof connected to that specific file. This makes it much harder for me to deny that I signed it later. You see, within the Create Digital Signatures interface, all the keys created previously from the asymmetric key generation interface are shown as also stored in this interface to be used to create digital signatures. Any hash file that was created in the past from the interface called compute SHA-256 hash is also available below to be digitally signed. So now we're going to sign the hash file that we just computed. Now I'm going to select the private key I just created listed above to create a new digital signature. After selecting the correct private key, I will now select the name of the hash file that I just computed that is listed below in the interface. After getting prompted, we will press yes to digitally signing the hash file, and to initiate the signature, I will type in the correct password associated with the private key. There it is. I have successfully digitally signed the hash file, and it will be moved to the next interface called Digitally Signed Files. Let's explore the interface I created called Digitally Signed Files. Within the Digitally Signed Files interface, the user has three main action options: verifying a digitally signed hash file, exporting the signed hash file with the corresponding hash file and public key used for verification, and deleting a specific digitally signed file. This verify button is used to confirm that the digital signature I generated is valid before exporting or sharing the signed hash file. It acts as a local validation and quality control step by checking the signature against the saved hash file and the corresponding public key. In a real non-repudiation workflow, the receiving party would still verify the signature independently using the signer's trusted public key. Aha! After verifying it, my interface shows that this is a good signature from John Doe. Let's say I need to email this file to my friend to add him to the chain of custody. We'll call him Leon Smith Anderson. In this situation, I need to export the matching set containing the digitally signed file, computed hash file, and public key file. Okay, after pressing export set, we have exported the matching digitally signed file, hash file, and public key. Let's check File Explorer for these important files. Here's the matching set of files we need to email together to Leon Smith Anderson. Now we're going to email our imaginary friend. Now we are going to attach all the necessary files to the email draft. Okay, now let's pretend we are Leon Smith Anderson and switch to his perspective. First, I'm going to delete the files we just exported so I can prepare to act as our trusted friend Leon. This is the fun part. Now we are going to verify the digitally signed email using the hash, digital signature, and public key. We can confirm that the document has integrity and that it was signed by the expected sender. Leon can view this NDA document, and at first glance it appears legitimate. However, Leon follows safe cybersecurity procedures and does not trust this document based only on appearance. For this demonstration, Leon will use the same GPG verification application to confirm the document's integrity, authenticity, and non-repudiation. Since Leon uses the same software, which is a modified version of GPG, he can use the interface I created called Verify Digital Signature to load the files received by email and verify the digitally signed hash file. Before verifying a digital signature with a public key, it is important to understand that non-repudiation depends on two key factors. The sender's private key must remain secure, and the public key must be trusted as belonging to the real sender. Before Leon verifies the digital signature, he first needs to validate the sender's public key fingerprint. This step helps confirm that the public key truly belongs to the claimed sender and has not been replaced by an attacker's key. Once Leon confirms that the fingerprint matches a trusted source, he can certify the public key and use it to verify the digital signature. Without establishing trust in the public key's identity, signature verification can still confirm the file integrity, but the sender's authenticity remains unreliable. Leon is going to start by using the interface I created called Verify and Certify Public Key. Leon is now going to load the public key he received from me by email. Leon loaded my public key. Now that the public key is loaded into the queue, Leon needs to verify that the fingerprint matches the fingerprint from his trusted source. Since Leon and I work for the same organization, he knows that he can verify the fingerprint of the public key I shared with him by comparing it against the fingerprint published on the organization's trusted webpage. This allows Leon to validate the authenticity of the public key's origin. If the fingerprint of the public key in his possession matches the fingerprint displayed on the organization's trusted source, he can be confident that the public key genuinely belongs to the intended sender and has not been replaced or tampered with. These are the fingerprint verification results for the key Leon received from me by email. Now that Leon has the fingerprint, he is going to compare it against a trusted organizational website. While Leon compares the fingerprint from the key against a trusted organizational webpage, he notices that the fingerprint and every detail about the organization's public key are an exact match to the verification results shown in the application. After Leon confirms the public key genuinely belongs to the intended sender, he can establish trust in the key by certifying it. He does this by digitally signing the public key with his own private key, which records that Leon has verified the key owner's identity and trusts the key's authenticity. Now that Leon has established trust in the public key by certifying it, the application imports and saves that certified public key into Leon's normal GPG keyring. So when Leon verifies a digital signature in the future, GPG can match the signature to the correct public key, confirm the signatures cryptographically, and show that the key is trusted because Leon previously certified it. The application will now allow Leon to export a copy of the certified public key and import it into his keyring. There we go. Now Leon is ready to verify the digitally signed file using his newly certified public key. Leon's next step in the process to verify the integrity of the hash file and confirm that the digital signature was created by the private key associated with the trusted public key. First, we are going to load the digitally signed file into the interface. Now we are going to copy the file path of the digitally signed file. Okay, next we are going to load the hash file. Finally, Leon needs to load the certified public key into the interface to verify the digital signature. Now that Leon has all three required files loaded into the interface, the Verify Digital Signature button is enabled. After verifying the digitally signed file, the verification results show a good signature. This means the integrity of the hash file has been confirmed because the hash file has not been altered since it was signed. Since Leon previously verified and certified the signer's public key, he can also trust that the signature is associated with the correct signer. However, this does not yet prove that the contract file itself matches the signed hash. Leon now needs to compute a SHA-256 hash of the non-disclosure agreement contract received in the email to ensure that the contract's computed hash matches the hash value inside the verified hash file. As you saw in the earlier demonstration, I was able to compute a SHA-256 hash file in my application. This is good news for Leon because he uses the same cybersecurity application as me. Leon is now going to fetch the file path of the non-disclosure agreement from earlier. Okay, now that the original file is loaded, Leon is going to compute its hash value. Now that the contract hash has been computed, let's verify the results and compare them against the verified hash value received in the email. After Leon computes the SHA-256 hash, the application automatically brings him inside the stored hash files interface. Leon now knows this is the hash value of the contract received in the email. But the final question is whether it matches the hash value Leon received from me in the email. This is the hash value associated with the hash file received in the email. Let's conduct the final review. Both hash values are an exact match. The newly computed SHA-256 hash of the contract matches the verified hash value from the signed hash file, confirming that the contract is byte for byte unchanged and has not been modified. Because the signed hash file produced a good signature using the sender's trusted public key, Leon can also trust the authenticity of the sender. Everything I have demonstrated so far represents the original goal of this project, using GPG-based graphical user interface to demonstrate non-repudiation, integrity, authenticity, and public key trust. As the project progressed, I decided to expand the application further by adding more GPG functionality into a user-friendly GUI. Cryptography is one area of cybersecurity I am most passionate about, so I wanted this application to go beyond digital signatures. To push the project further, I added the ability to encrypt and decrypt files directly through the interface, allowing users to protect the confidentiality of sensitive data without manually entering GPG commands in the terminal. In my application, I can perform these tasks inside the interface called encrypting/decrypting files. Inside the encrypting/decrypting files graphical user interface, the application supports two cryptographic methods: asymmetric encryption and decryption, and symmetric encryption and decryption. Asymmetric cryptography uses a public/private key pair, while symmetric cryptography uses the same shared secret to encrypt and decrypt the file. First, we are going to demonstrate asymmetric encryption in the application from our imaginary coworker, Leon's perspective. Leon wants to send Jesse an encrypted message, but first he needs access to the organization's trusted public key. So Leon is going to access the public key listed on the organization's website. This demonstration assumes that the organization follows secure web application practices, including strong access control for website administrators, protection against unauthorized content changes, secure hosting, HTTPS/TLS for encrypted communication, and regular monitoring to ensure the published public key has not been tampered with. Before Leon downloads or uses the public key, he needs to read the organization's safe procedure for using the public key file for encryption. The website says the public key files listed below are officially published by Chalif Penetration Testing. Download in and import the key into your keyring to enable encrypted communication. Always verify the fingerprint on the verification page after importing. Now that Leon knows he needs to verify the key's fingerprint, he initiates the download. Leon now needs to verify the fingerprint of the key before using it for encryption. So first, he's going to verify it again in the graphical user interface. Next, Leon will load the public key that he downloaded from the organization's trusted web application. This step allows him to inspect the key's fingerprint and verify that the public key has not been tampered with before trusting it for cryptographic operations. Great. We can now view the fingerprint of the downloaded key and compare it to the organization's trusted web application. Based on Leon's comparison, it is an exact match. Now the public key is ready to be certified. Now that Leon has downloaded the required public key and verified its fingerprint against the organization's trusted source, he can send me encrypted messages. Leon just needs to copy the file path of the public key he just certified. It is time to start the asymmetric encryption process. The certified public key is now loaded, so Leon needs to paste the file path of the file he wants to encrypt. The file has been successfully encrypted. The encrypted file that Leon wants to email me saved in the encrypted/decrypted files graphical user interface. In my application, when a user encrypts or decrypts a file, the user, which is Leon right now, is automatically brought to where the encrypted file is saved. Leon will now export the encrypted file and email it to me. Try this out. How? And send. Okay, now that Leon sent me the email, we are going to switch back to my perspective. I am the only one who has the private key that can decrypt Leon's encrypted message. In the application, I can use my private key to decrypt Leon's messages since I have the corresponding private key for the public key Leon used to encrypt it. Alright, let's start the asymmetric decryption. I just need to make sure I choose the correct private key to decrypt the file. Now that we selected the key, we will paste the file path of the encrypted message Leon sent us. Finally, to initiate the decryption, we just have to type the correct passphrase for the private key. After the file has been decrypted with our private key, it is automatically stored in the encrypted/decrypted files interface. Now let's see what our friend Leon sent me. This is the decrypted message. In my previous demonstration, I showed how my graphical user interface can perform asymmetric encryption and asymmetric decryption. Next, within the same encryption and decryption interface, I will demonstrate how the application can also perform symmetric encryption and symmetric decryption. Before I demonstrate that feature, I want to explain the difference between these two cryptographic methods. Asymmetric cryptography uses a public/private key pair. The public key can be shared and used to encrypt data, while only the matching private key can decrypt it. This is useful when secure communication is needed between different parties because the private key does not have to be shared. Symmetric encryption works differently because the same secret, such as a passphrase or symmetric key, is used to encrypt and decrypt the file. Because of that, symmetric encryption is best used when the secret is kept private and is not shared with unauthorized parties. In this application, I added a symmetric encryption option so I can protect confidential data stored locally on my computer. This is an example of protecting data at rest, where the encrypted files are not intended to be shared with external parties, and only I should have access to the secret needed to decrypt them. Knowing that, let's begin. Once again, we are going to copy the file paths. After selecting the file to encrypt, the user must enter a private passphrase. This passphrase is used to derive the symmetric encryption key that AES uses to encrypt the file's contents. The encrypted output depends on the key derived from the passphrase, the contents of the original file, and cryptographic values such as a salt or initialization vector. Because the passphrase is kept private and is not shared with anyone, an external user cannot decrypt the file unless they know the exact passphrase. The file has been successfully encrypted. The encrypted file is automatically saved within the encrypted/decrypted files interface. Now I am going to decrypt this file so I can view its contents. This is what the file contents look like after encryption. I am going to copy the encrypted file's path. This is an example of symmetric decryption within my application. The application has prompted me for the secret passphrase, so I am going to type the same secret passphrase I used to encrypt the file. There. Let's export the file from the encrypted/decrypted files interface and review the decrypted results. The file was decrypted successfully. That is it, the decrypted file. I love cryptography because it makes me feel like I'm in a spy movie, and it increases my ability to protect myself from malicious cyber actors. That concludes every cybersecurity task that can be conducted in my GPG Cryptography Toolkit application. Thank you for watching my video. Have a safe day, and always stay safe digitally. Goodbye. By the way, if anyone is interested in using my GPG Cryptographic Security Toolkit application, I have provided a link to my GitHub repository in the description of this YouTube video below. The repository allows anyone to download the required files. My GitHub repository also includes clear instructions on how to run the application after downloading the necessary materials. Anyone is free to modify the code, improve the application, or enhance its functionality. If someone can make it better, that would be great, and I would be happy to use the improved version.